Hello everybody, and welcome to Alan Wall's Photography. This is Alan, and you're watching the Circle of Confusion episode number 3, The Paradox of Sharpness. So what is the sharpness paradox? It's something that sums up questions that I get all the time about aperture and sharpness. It goes something like this. Why does my image become sharper as I begin to close down the aperture on my lens? And then if I continue to close it down, I lose that sharpness and the image starts to get soft again. So what is going on? It's a paradox because on the surface, it's a little bit confusing. You would expect that if there was one thing going on, that as you either increased or decreased the size of the aperture, that effect would increase or decrease proportionally. But that's not what we see. The very low apertures lead to softness, as do the very high apertures, and somewhere in the middle is a sweet spot for the lens. So what's going on? So let's first consider the very small aperture. As light passes through a small hole, like your aperture in your lens, it is diffracted, meaning the light waves are deformed and the light spreads out into a fan-like pattern. Now, when you change the direction of light waves, they are going to begin to interfere with one another when they cross. And the way light interferes with light is much the same way as waves in water interfere with one another. But when the peaks of the light waves encounter one another, you get a larger peak. When two troughs encounter one another, you get a deeper trough. But when a trough and a I forgot which hand was my trough. When the trough and the peak encounter one another, they tend to cancel the energy out. So what you end up with when light interferes with itself is an interference pattern which can be represented in 2 dimensions as a disk that consists of a bright disk surrounded by concentric circles of light and dark, with the light areas getting gradually dimmer. Well, when we talk about photography, we're really most interested in that central disk, and it's defined as the edge of the first dark ring around the central bright spot. And that is called the Airy disk, after a guy named, I think it was George Airy. One way to think of this Airy disk is as a fundamental unit of sharpness or resolution. So let's recap that. When light is diffracted, it results in a representation of a point in space as a disk of light on your sensor. As the aperture gets smaller, the Airy disk gets larger and excites more adjacent pixels, which means that the point in space that should be, hopefully, showing up as a point on your sensor is now showing up as a bunch of points on your sensor or a blur. And that is what limits resolution in all photography. Now, another interesting thing about Airy disks and diffraction is that only 2 things determine the size of an Airy disk, and this is important. Those 2 things are the aperture and the wavelength of the light. One really critical thing to remember, even though it may not have a practical impact on your photography, but any aperture causes diffraction. Even an infinitely large aperture will have an edge, and that edge will diffract the light. But when the vast majority of the light is passing parallel as a flux through the aperture opening, and only a tiny amount is reaching the edges of the aperture, the effect is unnoticeable. So if this was all that was going on, you would think that all you have to do is open up your aperture as wide as you can get it. That will mean very little light is encountering the edges of the aperture, and your picture will be as sharp as it possibly can be. And in theory, that would be correct if there wasn't something else going on. But there is something else going on. That something else is called aberration. So what exactly is an aberration, and how does that differ from diffraction? You've heard me talk before about an ideal or a perfect lens, or a flat lens sometimes. That is a theoretical lens. It's a lens you draw out on paper that allows you to make precise calculations based on properties of a lens that don't actually exist in nature. It's just a way to simplify the calculations of optics and to give you an idea of where the light would go in the perfect case. No lens is perfect. No lens is ideal. All lenses have a greater or lesser degree of variance from that perfect ideal lens. And anything that causes light to behave differently than in the ideal model is an aberration. Now, you're familiar with chromatic aberrations. We talk about that. Well, we haven't really done a deep dive into it, but now as I just thought about it, we will. There are two general categories of chromatic aberrations, and they are axial and lateral. And that is how different wavelengths interact, different wavelengths of light, different light energies interact differently with the elements of the lens as they pass through. We're not going to focus much on that. We're going to talk about the non-chromatic aberrations. These are things like spherical aberration, comma aberration, which is kind of off-axis aberration. Field curvature is another one. Astigmatism is another one. These are all terms that describe ways that light can travel through a lens that differ from how the light would travel through a perfect lens. And the end result for all of them is the same. Well, that's a dangerous statement. The end result to all of these aberrations is manifest in much the same way. And that is that the point in space that we're photographing is not represented as a point on the sensor because of the aberrations. Let's take an aberration like the comma aberration, where because of the way light travels through the center of a lens differently than it does at the edge of a lens, it results in the representation of the point in space on the sensor as what looks like a comma. So think of it this way. With the ideal lens, a spot in space will show up as a spot on your sensor. Perfect world, ideal lens. But as a result of aberrations, the spot in space is not showing up as a spot on your sensor. It's showing up as a stretched out blob, or a blob with a bit coming off the top. There's all kinds of ways that aberrations manifest. They change the shape of the point in space depending on the aberration and how severe it is. Now, what's important is that as the shape and the size of the representation of the point in space on your sensor gets larger, it starts to excite more pixels again. So the final common pathway is that instead of just exciting one pixel, the aberrations in the lens result in more pixels getting activated and a less resolved image. Now, this is another huge generalization, but it does serve the purpose here. Aberrations get worse as you get closer to the edges of the lens. As you're using more and more of the lens, you are more likely to introduce significant aberrations. All lenses have aberrations. Some of them have less, some of them have more. It's the expensive ones, by the way. This is a pro tip. The expensive ones usually have less. But for the time being, just consider this, that the more of the lens that is seeing the light as it goes through on its way to the sensor, the more impactful the aberrations are going to be. So how can you reduce the aberrations that are causing blurriness in your image? Use less of the lens. Shut down the aperture. And that's exactly what happens. As we close the aperture, the majority of the light is then passing through what is usually the purest optically part of the lens, which is the center. So as you close down the aperture and most of the light now is going through the part of the lens with the least tendency to introduce aberrations, your picture gets sharper. It gets sharper because our point in space is, for a brief period of time around f8 or f11, is being represented as a single point on the sensor. And that explains the paradox of sharpness. There's one other thing I would mention before I go, is that is not all sharpness is about. There are other things that contribute to our ability to perceive an image as sharp. Edge contrast is one of those things. Another is whether or not our image is in focus. And we haven't really talked about that, because in all the examples I gave, everything I've said about diffraction and aberration assumed that the point in space we're talking about is focused on the sensor. As you defocus, as the point moves in front or behind the sensor, that will of course cause softening, but that's completely different, and we don't consider that an aberration, because if we move the lens, it'll come into focus. So it's not an issue with the lens, it's an issue with the position of the lens. That's enough for one day, for one answer. I hope this was helpful to you if you've been struggling with this question. Oh, I've got so much stuff coming up, I don't even know what to tell you about. Go over to Discord, they're waiting for you over there. I'll put a link for you to join in the show notes here. Thank you so much to all my Patreon supporters. I really, really appreciate you, and to the folks who've contributed through the website, thank you. And for sure, if you have a question that you would like to hear discussed in a future Circle of Confusion, please let me know. Always looking for interesting stuff to talk about. Thank you for watching, thank you for liking and subscribing, and thank you for just being you. Please avoid the viruses, and I'll see you in a day or two. Take care. Goodbye.